All right, good morning, everybody. So we are pleased to have our third scientific organizer, David Poland, has joined us. He'll be lecturing next week, but I'll turn it over to him to introduce Netta.
All right, thank you, Oliver, and it's great to be here. So this week was designed as a quantum gravity-focused week, which is an important thread running through the theory tapestry. And our first lecturer today will be Netta Engelhardt, who's going from MIT, who's going to tell us all about black holes and what may be beyond their horizons.
Perhaps. All right, thank you very much for the invitation. I've never actually been physically in Tossie before. I had the virtual experience a couple of years ago, so it's a pleasure to be here. Now, some of you may be looking and thinking, that's not Tom Faulkner. It doesn't look like Tom Faulkner, the title doesn't sound like Tom Faulkner's title, and you would be right. So if you showed up here for Tom Faulkner, you will have to wait until 10:45. And so if you have no interest in black hole information, I won't be offended if you now decide to go from the front row and move to the back and take a nap. That's quite all right. All right, so I've been assigned the topic of black hole information, or heavily suggested that I talk about black hole information, which is it's a 50-year-old problem. And you could say, okay, 50 years old, you could still talk about it in 4 lectures. But even though it's only 50 years old or 50 years young, depending on how you want to think about it, there's just been a tremendous amount of work that's been done on it. It's generated just a huge amount of intellectual work, tangentially related, directly related, essential, maybe essential sometime in the future, maybe inessential. And so 4 lectures are just nowhere near enough for me to even begin to cover the essentials of this problem. And so what I'm going to do is I'm going to take a very particular approach. I'm going to highlight and emphasize certain things over others. And I'm going to be schematic. I'm going to make approximations. I am going to say something is roughly speaking like another thing. And I promise you that there is solid, rigorous reasoning behind all of that. I'm happy to point you to references. But in many places, I will simply have to say, we're going to use some approximation or some idealization to see the intuition behind how this works. And as long as adding in the technical details doesn't dramatically change the conceptual clarity, I won't be doing it. And that's just what we have. You'll notice that I have 5 things here at 4 lectures. It's called optimism. OK, so without further ado, I'm going to begin with the problem, which was formulated by Hawking in 1975. Now, the problem of black hole information is rooted in black hole thermodynamics, which you guys all studied last week. So I won't be introducing the subject of black hole thermodynamics. I assume everyone diligently attended Luca's lectures. However, there will be a difference between how I approach black hole thermodynamics and what you studied last week based on what I can tell from the notes. And the difference is that we're going to be interested in dynamically evolving black holes, primarily ones formed from collapse. And that in particular means that Euclidean preparations will be less valuable to us, at least insofar as the geometry goes. Nevertheless, there are various approximations that we can make, such as when a black hole has equilibrated and is very close to being some slice of Schwarzschild, and that's when we'll be able to talk a little bit more about the Euclidean picture. But things will be different on account of the black holes that we're interested in being formed from collapse. And we're going to be interested in black holes that form from collapse and at late times when they're no longer accreting. So again, they're kind of evolving very adiabatically. They're roughly speaking at equilibrium. And so let's begin with the problem. Now, the references for these first 2, I'm primarily using a little bit of my own notes, which I will eventually post, and also Daniel Harlow's Jerusalem lecture notes. I have the archive number written down here. At times, I'll deviate from these when I think that the more modern perspective, these are from 2014, calls for a slightly different approach. and this will be good for this and that, and then when we get to this, we'll sort of go off script. And that'll all happen in this lecture. All right. Okay, great. So I said that we're going to talk about black holes formed from collapse. So let me just remind you of the toy model we like to use for black holes formed from collapse, which is the Vidia spacetime. So it's idealized in the sense that we have a single shock coming in and forming a black hole. But for our purposes, again, we're going to idealize things without taking away from the essentials. That'll be exactly what we want to think about. So a black hole formed from collapse. This is the Vidia spacetime. Here we have I minus, I plus, I zero, scry minus, and scry plus over here. So here we have the Schwarzschild region up here, and we have the Minkowski region over here. We can write this down in Eddington-Finkelstein coordinates if you want to write a metric everywhere with some mass function. This is ingoing Eddington-Finkelstein coordinates plus 2 dV/dr plus r squared d omega squared. And mostly we'll be working with the Schwarzschild region up here. So we're not really going to be using the Eddington-Finkelstein coordinates. We're just going to be using standard Schwarzschild most of the time. So this is kind of, to keep in mind, this is the metric everywhere. But since we're going to be focusing on the region after the black hole's formed and once it stopped accreting and settled down, then we're going to be mostly using the Schwarzschild metric. I know you guys all know this, just reminding you because it's early in the morning. Okay, so last week you learned from Luca that the Schwarzschild black hole has a temperature, right? It's inversely proportional to its mass in natural units. That's the temperature in the Hartle-Hawking state, 1 over 8 pi m. Now, in a Hartle-Hawking state, this is a consequence of having, you have ingoing modes coming across one horizon, and you have outgoing modes a tangle across a different horizon. We're going to go through this derivation a little bit more in detail in a moment. But once we're in this region over here, we're not really in the Hartle-Hawking state because we don't have ingoing modes anymore. Right? I just told you we're not throwing anything else in anymore. We've waited, the black hole has fully settled down, and there's nothing coming in from the asymptotic boundary. And so this temperature that the black hole has is purely as a result of the outgoing modes, the modes that are moving in this direction. So this temperature here, in this case, for an accreting black hole, and we're going to go through this. I'm giving sort of a broad overview now, and we're going to go through this in detail in a bit. This is purely due to outgoing modes. Now, there's sometimes a confusion where I say this is an outgoing mode, and you could say that's behind the horizon, how can it be outgoing? We'll literally just mean it's the right moving mode here. That's a terminology that we use, outgoing, as opposed to one that's just moving towards progressively smaller spheres over here. Okay? So that's literally what we mean. That's what outgoing and ingoing means over here. So just looking at this, and again, this is very broad brushstrokes, we can say, okay, so there's nothing going into the black hole because we don't have any ingoing modes. They're all in the vacuum state, in the ground state. We do have outgoing modes, which means there's going to be a net flux of energy away from the black hole because we have radiation out, but we don't have radiation coming in or stuff coming in from the boundary, which tells us that there's going to be, again, there's going to be energy moving out. And we have conservation of the total energy in the space-time in terms of the ADM Hamiltonian. So the ADM mass is something we measure asymptotically. And it tells us that the mass of the black hole, roughly speaking, plus what we have in the radiation, that has to be conserved. Which means if there's energy moving away from the black hole, the mass of the black hole and the size of the black hole had better shrink. And that is how we show, roughly speaking, that the black hole is really evaporating. It is shrinking in time as a consequence of the radiation. Now, Let's see, am I brave enough to attempt to bring this up? Yes, I am. All right. All right, almost there. Okay. All right, so we say, okay, the black hole is shrinking, and we have the state of the radiation moving out. Now, the radiation, we said it has a temperature, so it's in a thermal state. Yes? That means that if we start out, so let me draw a diagram of what it looks like when the black hole evaporates. So this is R equals 0 over here. So we have initially what we had over there is we had scribe plus that way. Here we have, draw a different way. Okay, so here we have our black hole. Now we say it evaporates at some point, which means at some point the event horizon goes away. And so we have some region up here where there's no event horizon. And eventually this region gets to future infinity, I plus. And so the diagram needs to look something like this. 0, I minus, where here we have all of these outgoing modes. Now, because the outgoing modes are in a thermal state, something we'll derive in a minute. So you can sort of intuit it from the Hawking state over there. That tells us that we end up with a thermal state up here, which is a very heavily mixed state. But if we prepared this black hole by throwing in a pure state, and we ended up over here with something mixed, then we find that time evolution takes a pure state and sends it to a mixed state. In fact, it sends it to a thermal state, which if this is Schwarzschild over here, is really just distinguished by the mass of the original black hole, the total energy. Okay, so first of all, this immediately says this is a non-unitary process. And a lot of people just stop here, saying, okay, that's bad, quantum mechanics is unitary. But I think it's worth asking, why is that so awful? So maybe we have to give up unitarity. Why is that so bad? And the answer is that we lose determinism, if that's the case. Not because this non-unitary processes are necessarily are non-deterministic, but because this particular process will take 17 stars formed from different pure states, which all have the same macroscopic properties, the same mass of the black hole that they form. And it will produce for us 17 copies of the same thermal state. So we get rho, let's call it beta, the only thing that matters here is temperature. We got 17 of these. The number 17 is a random number that I picked. We could have picked 63 or 5 or 247, or any other number you like, as long as it's a total. As long as it's an integer. Yeah. Okay. So what's going to happen is it takes all of these states, which are all different, and it's going to map them all to the same state. And now suppose we look at the end product. We're looking at some kind of maybe look at the S matrix, right? We look at the end product and we say, oh. I have 17 identical states. There is literally no deterministic process that I can take to get 17 initial states which are different, right? I have my time evolution. If I would try to run my time evolution backwards, then I start out with the same state. I'd better get the same state back if it's deterministic. And so the problem with a particular non-unitary process is that we lose predictivity of physics. And that is a catastrophe because physics is supposed to be a predictive science. And so there is a lot at stake. Okay, so, I see a question, yes?
Why do you expect all of them are the same? Shouldn't there be something like epsilon close to that thermal state?
That's a great question. So so you're asking about something that we'll mention, which is called the small corrections theorem. As it turns out, these are going to be the same thermal state. This is essentially a consequence of the black hole no-hair theorem, or no-hair result. That these are all going to be the same. You might worry that small corrections might somehow help you here, and it turns out that they don't, and we can prove it. This is a theorem due to Samir Mathur. So yeah, question? Yes, I will absolutely write bigger. Yeah, other questions? All right. Let's see where we're at. Okay. So what I want to start with is a rough derivation of the statement that we have the left movers here are in the ground state and the right movers are in the thermal state. And the way we're going to do this is not the way that Hawking initially did it. Hawking worked very hard to work 100% at all times in Lorentzian signature, which is an admirable thing to do, but there are shortcuts. And we're going to use approximations that allow us to work a little bit in Euclidean signature. And as it turns out, these shortcuts do make approximations, but those approximations do not matter, not qualitatively. OK. I'm not even going to attempt to move this board again. And instead, I'll go this way. OK. So we'll begin. With the Rindler decomposition. So our modus operandi here is going to be to use the fact that the black hole, once it's equilibrated up here, everything is nice and smooth. This, roughly speaking, looks like Rindler space. And we're going to do our calculations in Rindler space, and then we're going to map them to the black hole, and we're going to see how they work out. So we're going to make a little observation here, which is that the Schwarzschild metric that I wrote down over here, if you do a near horizon expansion, you get the Rindler metric. So see how that works. We're going to use the following coordinate substitution. So epsilon is going to be our new coordinate. We're working with in the limit where epsilon is very small, so we're very close to the horizon. And let's see, dr is going to be 4m epsilon d epsilon, and f of r are going to be approximately epsilon squared once we do a Taylor expansion. And under this coordinate change, the metric is going to be this plus subleading corrections in epsilon. And now I'm just going to do a slight redefinition. I'm going to push this 16m squared over to this side. Sorry, one of these is an epsilon and the other is a t. Sorry about that. So this, I'm going to do a slight coordinate redefinition. And I'm going to also change this. I'm going to call this eta for no reason other than I feel like it. And I'm going to redefine a new variable as 1 over 4m. C over 4m is going to equal epsilon so that I can push this term over here for reasons that will become obvious momentarily. And I really could have done that already up here, but oh well. All right, so this is going to be c squared over 16m squared d eta squared plus dc squared plus 4m squared d omega squared plus subleading corrections. Now, this line element over here is 1 plus 1d Rindler space. Now, how many of you have studied Rindler space to the point where you can just regurgitate everything that you see about, you know about Rindler when someone wakes you up in the middle of the night? A few of you, yeah. It's something that you often study like at some point, maybe you take special relativity and you kind of never see it again. So I'm going to do a very kind of lightning review. It's OK if you haven't seen it before. We're going to review it now. All right, so this is Rindler space, which is just a different coordinate patch for Minkowski space. And it's a coordinate patch that's particularly suited to describing the experience of a uniformly accelerated observer. So a uniformly accelerated observer is going to have a constant c trajectories with a proper acceleration that is 1 over 4m in these for this particular choice of Rindler metric. Otherwise, you will have simply the 1 over the proper. This is going to be multiplied by the proper acceleration over here. So let's go into a little bit more detail on that. So this is Rindler space, and in particular, adapted to a uniformly accelerating observer with proper acceleration (1 over 4m). Can everyone still read that out there? Does it still need to be bigger? Just do this if it needs to be bigger. Okay. All right. I will work harder on this. Okay. So what is Rindler again? So I said that Rindler is adapted to the coordinates of a uniformly accelerating observer. So let's just start out with 1 plus 1D Minkowski space. And we're going to just implement a coordinate transformation. So this is, we can see, okay, so this is for a proper acceleration, which is equal to 1. Otherwise, you put a little a over here. And t is going to be c sinh eta. So c minus t squared, x minus t squared is c squared. And this, in Minkowski space, measures proper distance from the origin, right, along straight lines, which are space-like geodesics. So, or geodesics in general. So that tells us exactly what Rindler space is. So Rindler space covers the left and right wedges here. So this is what we get when we remember that this has to be greater than or equal to 0 over here. So this is a constant proper distance from the origin, proper distance, not proper time, which means that we're going to be space-like separated from the origin. And the constant c trajectories basically look like this, where where the proper time along these is going to be measured by eta. Eta is the parameter that ticks along these to measure the observer's time. Now, let me. So an observer at some c equals 1 over a is going to be an observer whose with uniform acceleration a, and the proper time measured along the trajectory is just going to be d tau squared, which is going to be 1 over a squared d eta squared. So a rescaling of eta is measuring the proper time along the trajectory. Now, eta this vector here is actually going to be generating boosts. The way we can see this is we can say this thing here is a constant proper distance from the origin. And the fact that it's a constant proper distance from the origin means that it is invariant under everything that leaves the proper distance interval invariant, which is the Lorentz group. And so that tells us that this thing is going to be invariant under Lorentz boosts. But the way that we slide along this thing is with eta. So just 1 second. So the eta vector, so this vector here is the boost vector in Minkowski space. Yes?
You just said a is equal to 1, so this because a is equal to 1 of a, which is also equal to 1.
So for a equals 1, then we're just talking about then it's just eta, sure. But otherwise, you just rescale it if you wanted to generate boost for a different for a different hyperbola for a different c. So the vector itself is still the same. It's still the same vector. It's just rescaled. Does that answer your question? Great. Other questions? Okay. Great. Okay. So so this, if you'd like, you can show this on for yourself. You can show. This is not too difficult to show that this is just the boost vector. You can just transform back to Minkowski space and see that this thing generates boosts. Okay. So much for special relativity, and let's do a little bit of quantum field theory. What we're interested in ultimately is going to be the behavior of quantum fields on Rindler space, because that's going to map very closely to the behavior of quantum fields across this horizon over here. So that's the big picture. And we're going to start with something very simple. We're just going to say we would like to write down the Minkowski vacuum in terms of boost eigenstates. Right? This just in terms of, left and right boost eigenstates over here. And the reason that we're interested in doing that is in part because even though this is the boost vector, and the operator that generates boosts is it's going to be given by this, we can also think of this as the Hamiltonian for a Rindler observer, because this generates time translations. Right? This is the time translation generator for Rindler observers. So this is also time translations. For a Rindler observer. Okay, so what we want to do is you're going to just write out the vacuum state, the Minkowski vacuum. I'm going to write it as a density matrix. It's just a little more convenient that way. In terms of Rindler energy eigenstates. I'm sporadically remembering that I need to write larger, which is what is responsible for the varying sizes of words. Okay, so the first thing we're going to do is we're going to remember that one very easy way to prepare the vacuum is to take any state and to just evolve it for a very, very long Euclidean time. That is going to just kill all of your excitations and eventually give you the vacuum. So let's suppose we're working in 1 + 1 dimensions. We have some QFT on a line. And we would like to prepare the vacuum. And as I said, we're going to go to Euclidean time. So schematically, and by which I mean without normalization factors, this is just going to be the path integral, where here we've gone to minus infinite time over here. So if you prefer equations, you can just think of this as something like minus t Euclidean times the Hamiltonian of some whatever state you want to start out with in the limit that t goes to infinity. So this is the path integral. This is just the in terms of words. Okay, so this is what we're going to start out with. Now, it turns out it's going to be a little bit easier for us to actually first look at the reduced density matrix of the right wedge or the left wedge. I'm not going to work with the right wedge, but of course they're completely symmetric. And write that out in terms of the energy eigenstates, the Rindler energy eigenstates. And then we're going to eventually get back to the state of the vacuum, which is just going to be the state of the whole thing. Okay, so the right Rindler wedge is just going to be the trace over the left Rindler wedge of rho, or rho is, where did I definitely wrote down the vacuum state somewhere. All right. Rho, oh, there it is, okay. Okay, so we're interested in doing this. Now, in terms of the path integral, what this means is we're going to do a sum over the fields that are localized in the left wedge. So here I'm going to, so this is right, this is left. So these are in the left Rindler wedge. And for a density matrix, I have 2 copies. All right, so here I'm taking a trace over the phi tildes. And this I'm leaving unspecified since I have a density matrix over here. Okay, so this is what I'm interested in doing over here in order to write down the density matrix. So if I haven't done anything in terms of the Rindler eigenbasis, I'm just making it a little bit more suggestive by dividing this up into left and right Rindler wedges. Okay, now the key observation here comes when we, here, okay, so the key observation comes when we want to compute this quantity. For some, you have some fields, phi1 and phi2, and we are going to essentially represent phi r on these two fields. So these are on just exclusively on the right Rindler wedge. Phi1 and phi2 are localized on the right Rindler wedge. Again, I'm tracing out over everything on the left Rindler wedge, and I'm cleverly going to ignore any UV-related issues at this point over here, because they turn out to be a pain to deal with and not change the answer overall. So this I can represent in this way. Just start with a square. This is phi1. This is phi2. And of course, implicitly, I have the phi tildes from before, but I'm summing over them. So it's irrelevant for me. That's what the trace is doing. The trace is doing the sum over here. All right. So now that I have this, this is evaluated from T Euclidean, goes from minus infinity to plus infinity. And the key observation here is to realize that there's another way to slice this thing. So one way to do it, of course, is just say, OK, I have my infinite x extent and my infinite t extent. And this is, of course, in Euclidean time. So the metric looks like this. But another way to slice the plane is in terms of polar coordinates. So I could also just slice this up like so. Meaning I could say, all right, I have some radial coordinate, and I've got an angle that I'm interested in. So I can rewrite this as just the theta, the r squared plus r squared theta squared. And that's a completely valid thing to do. And now I have theta going from 0 to 2 pi instead of t going from minus infinity to infinity. I haven't done anything, but it's actually a very useful observation. Just need a larger piece of chalk. OK. Now, this looks a lot like Rindler in Euclidean signature, right? If we just analytically continue theta to I eta, then we are going to get Rindler here. And that's the key observation. So theta is the Euclidean Rindler time. And it's periodically identified. Theta is identified with theta plus 2 pi. Now, this reslicing here, with this periodicity, tells us exactly one thing, which is that this is equal to, so we have the phi1 over here. This simply reduces, under this slicing, to the generator of rotations in theta for 2 pi of it. So that's just going to be E minus 2 pi h Rindler, which is the generator, phi2. And now we say, OK, and this is, I'm being a little schematic. This is equal to that, and therefore this must equal this. And so we find that rho r is going to equal e to the minus 2 pi h Rindler, which is a thermal state. It is thermal with respect to h Rindler, thermal with respect to the eta coordinate, which is the time coordinate for the Rindler Hamiltonian. And we can write this as 1 over z sum I e to the minus 2 pi omega I, where these are both on the right wedge. And it has a temperature as well of 1 over 2 pi. So this is on the right wedge. Now, how do we get the vacuum state. This is the vacuum state on the right Rindler wedge. It appears to be thermal in Rindler coordinates, and we're going to get into that shortly. But we can ask, okay, that's just the right wedge. What about the full vacuum? And there we just, I'm going to arm flail a little bit, and I'm going to say, well, the left wedge is just going to be a rotation of pi from the right wedge. And a rotation of pi in Euclidean signature is just CRT in Lorentzian signature. And so that tells us, very, very hand-wavy, but it does turn out to work exactly this way, that we can write down, maybe let me write this down as an actual state here. 0 is the usual thermal state, or thermal on each one of the wedges, where this is a CRT conjugate of that. So this is the Minkowski vacuum, the standard ground state, written out in terms of the eigenbasis, the energy eigenbasis of the Rindler Hamiltonian. Each one of these, so L and R, are in a thermal state with temperature 1 over 2 pi, which is unitless, which seems a little strange. Now, the reason that it's unitless and it's a temperature of just 1 over 2 pi is because we've secretly set A to 1 here. So you'll see we did this here, and in going to Rindler coordinates, we've just not introduced this factor of A, which would have given us an extra factor over here. And if you keep track of all of the factors of A as you switch to Rindler coordinates, you keep track of how eta is rescaled, then what you find that for a uniformly accelerated observer, with acceleration A, or in other words, Rindler coordinates adapted to this particular observer, the perceived temperature is A over 2 pi. And you can put, just 1 second, you can put the units in as well. Question?
How did we see here that H Rindler would have a discrete set of eigenstates? Is that because of the identification with the generator of H2?
Yeah, so how do you see that this generates the energy, that this generates this?
Or how do we see that it's a discrete spectrum?
That it's got a discrete spectrum. Oh, because theta is periodically identified. Yeah.
Lorentzian vacuum is one purification for rho r, and this is canonical purification for rho r. So why is the canonical purification just the Lorentzian vacuum?
So what we've used here is the fact that the right and left Rindler wedges are CRT conjugates of one another, the state in particular. So if we could have imagined that we have some different state in the left Rindler wedge, that would have been an alternative purification, but it would not have been the Minkowski vacuum. Because in the Minkowski vacuum, we have a symmetry between the left and the right, and this is CRT. Yeah. Mm-hmm. Other questions? Yeah. Would you? Sorry.
If I just thought about like free coordinate,
Yeah.
the right of which
Yes, you can 100%.
like wouldn't I get a continuous spectrum?
No, so you can do this for the free scalar, and do the decomposition, and because of the periodicity of this, so this works for the reason we do it like this and not for the free scalar is because it worked for arbitrary coupling. Because of the periodicity, it does work out for the free scalar. I'm happy to have the conversation about how that works out offline. Yeah. Okay. Yeah.
Why is the spectrum of the Rindler Hamiltonian bounded from below?
Why is it what?
Why is the spectrum of H Rindler bounded from below?
Why is it bounded from below? It is bounded from below for the same reason that the Minkowski one is bounded from below.
Because from the Euclidean perspective, I thought it's just rotation.
Yes.
But it could have like.
So it's the boost. So it also generates boost in Lorentzian signature. You can think of it as just the boost generator, and you can argue from that it has to be bounded from below as well. Yeah. Okay. All right, so let's see. Okay, so I'm going to say one or two more words about Rindler before we move to actual curved spacetime and black holes and not just a lesson in quantum field theory. So one thing you might notice here is that we have a lot of entanglement between the left and right Rindler wedges. So this is a highly entangled state between left and right Rindler wedges. So we could ask, so notice, rho L and rho R are heavily entangled. And it turns out that this entanglement between rho L and rho R is absolutely essential to having a smooth spacetime in between the two. Now, there are a couple of arguments you can make to this effect. The first is very hand-wavy, where you say, oh, suppose that we put the left and right Rindler wedges in what's called the Rindler vacuum. So the Rindler vacuum is the one where, so Rindler, 0 Rindler is just this state, where these again are the, in terms of the Rindler basis. So these are completely unentangled, uncorrelated. And a hand-wavy argument would say, well, if this wedge is not correlated with that wedge, then how can you possibly tell that they're connected in the first place? Right? You could say, okay, I'm going to go ahead and compute some kind of correlation functions if I want to, and I could see that, oh, there's no correlations between them, so there's no sense in which they're connected. So that seems that this is a very hand-wavy argument, so let me maybe make a somewhat more precise one before I take questions. So you could say, oh, there's no sense in which this could possibly be connected, and so there must be something that goes wrong at this point over here. Is it an urgent question, or should I? Okay, all right. Let me try to make a more precise argument now. Another way in which you could see that this is true, which is more reassuring than just saying, no correlations, ergo something bad happens, is you could, for example, take say, the regular scalar Hamiltonian, if you like, and just look at the kinetic term. So we can take a look at the kinetic term for the Hamiltonian of some scalar. And we can say, well, okay, this thing is going to diverge if the field is discontinuous somewhere. And if there's no correlations between the left and right Rindler wedges, then we expect that the field is going to fluctuate at the origin on an amount which is approximately the average field fluctuations, which is going to be set by the UV cutoff. And so we're going to expect that in general, for typical states without correlations between these two, when we go from this to that, we're going to have a very large discontinuity in the field. And that's going to lead to a very large energy that is concentrated here on this horizon. So what we find is that the entanglement between them is absolutely essential. Having correlations between the left and right Rindler wedges is essential for having something like a smooth transition between them, as measured, for example, by the Hamiltonian. Now, you can make this argument in a third way, which is to compute the expectation value of the stress tensor. So if you look at the vacuum subtracted expectation value of the stress tensor, you find that the difference over here between the Minkowski vacuum and the Rindler vacuum is infinite. So compared to the Minkowski vacuum, the Rindler vacuum will have a divergent stress tensor if you compute the expectation value in the Rindler. So you can come up with many different arguments. Some that are purely for free field theory, some are for arbitrary, for interacting theories. And it all says if you don't have this entanglement between the two sides, you're going to encounter something that is like, one might say, a wall of fire as you cross from one wedge to the other. And this is the basic mechanism that we'll see, hopefully we'll get to that, comes in for firewalls. So, okay. I think there was a question in the back, has been answered. Perfect. Other questions? Yes?
Would a specific form of this entanglement matter for this firewall?
Where's what, sorry?
A specific form of this entanglement matter for this?
Yes, absolutely. So you can argue that if you don't have exactly the right form of entanglement, like vacuum entanglement between these two, then you're going to, with high probability, still have enough fluctuations in this that you will still have a large shock, large energy shock. So yeah, not only does the amount of entanglement matter, but the quality of the entanglement matters as well. Yeah.
The vacuum state you wrote down is still in Euclidean time, right?
Is it what?
It's still in Euclidean time?
The vacuum state I wrote down here.
Yeah.
This is, I mean, the vacuum, you can prepare it so that's a t equals 0. So this is also the Lorentzian vacuum. Yeah. All right. Okay, so this is everything we need from Rindler. And we are ready to now apply what we've learned to black hole evaporation. Okay, so we have this picture over here of the evaporating black hole. And as I mentioned before, on timescales, on short timescales out here, we're going to approximately evaporate the black hole as static as long as we don't follow it for too long. And question.
I just have a naive question. So if I start with a Minkowski vacuum and go to a Rindler vacuum, is that a non-unitary process? Because I would assume so, right? Because
You want to do something very violent to the Minkowski vacuum. You need to break the entanglement.
yes, exactly.
And that's going to, so the way that you would do that is you would actually acquire a very large expectation value for the generator of boost. Exactly, that's right. So it's not a low energy process to jump from one to the other.
It is a non-unitary process, and hence the entanglement can be understood like that.
Yes, so it breaks the entanglement. It's a yes, right, yes, that's correct. Yeah. Okay, so when we're up here in this region, for short time scales, we're going to be approximating things as being approximately stationary. Of course, as we evolve in time, we'll need to pick a new stationary black hole each time because the black hole will have shrunk a little bit. But for short time scales, this approximation will work well for us. Okay, so let me actually redraw that picture over here. Okay, so let's ask, how does this, what we've done, map onto Minkowski space, or map onto Rindler space? So we can say, okay, at any point that we're looking at sort of over here, right? This is going to act. We know that the metric over here is just going to look like this, and so it's just going to be very much like Rindler over here. Now, this is for the right-moving modes, the outgoing modes. Now, for the left-moving modes, we have a somewhat different story because there's no past Rindler horizon here, right? This is sort of the future Rindler horizon for the right movers, but for the ingoing modes, the left movers, there's no past Rindler horizon. And of course, we want them to actually be in the vacuum because we're not throwing anything in. So from the perspective of an observer who's floating outside the black hole, observer who's floating outside the black hole is like a Rindler observer. They're accelerating in order to not fall in. And so from their perspective, the left movers are in a vacuum. And that tells us that the left movers here, the ingoing modes, are in the Rindler vacuum. And that means that, oh, there must be something terrible that happens across the past Rindler horizon when we finally get to it, because the left and right wedges are not entangled properly. But guess what? There's no past Rindler horizon here, right? This here is a point, and there is no past Rindler horizon we have to worry about. So it's okay for us to have the left-moving modes up here in the Rindler vacuum. There's no singularity that's going to come up as a result of that because there's no past Rindler horizon in this space-time here. If we were talking about Schwarzschild, on the other hand, we would have a very serious problem because there is a past horizon in Schwarzschild, and the left-moving modes would be singular on that horizon because we would have broken their entanglement. Is there a question? Sorry, where are we?
You're just taking the Rindler
Oh,
analogy.
yeah.
What's going on here? How would somebody in the right Rindler wedge ever know anything
They would not. They would, unless they stopped being a Rindler observer and jumped behind the Rindler horizon, they would certainly not know. But they certainly would know if they jumped and experienced a firewall when they jumped through the horizon. And as long as they're staying outside the horizon, they're just like a Rindler observer. Yes. So for someone who's just sitting just outside the horizon, all they're seeing is this is just because this, again, this space-time looks very much like Rindler, then we can approximate it. We can approximate it on short time scales as Rindler. And we have an observer who's sitting here who's just like a Rindler observer. So this is for the right moving modes. Now, for the left moving modes, we've imposed by hand that this black hole is no longer accreting. So nothing is falling in. So even an observer who's sitting out here and not jumping into the black hole can tell that there's no flux of radiation coming from scry minus. And so since an observer sitting here can tell that there's nothing coming in this way, then these left moving modes are going to be in the Rindler vacuum. The right moving modes, on the other hand, everything looks exactly like Rindler. And so we say the right moving modes are in a thermal state, right? This is the Minkowski vacuum, and in order to have a smooth horizon. And so they must be in a thermal state. So here we're assuming the horizon is smooth, of course, which again is something that's been called into question in recent years. So for the left movers, or the ingoing modes, we say, okay, so these must be in the Rindler vacuum. And then the right moving modes, these are thermal. And they have a temperature of A over 2 pi. And you ask, what is A? Well, A is 1 over 4m. That's what it takes to map this onto Minkowski space. We have to have this rescaling over here. And so we find, indeed, the temperature that we expect. This is the Hawking temperature. And so the black hole is in a thermal state, just like we have for the Hartle-Hawking state, but not the Hartle-Hawking state because we have the left movers that are going this way. So when the dust all settles, you can write down the state. Now, there is a bit of a complication, which is that the black hole actually has a bunch of gray body factors. The gray body factors result from the fact that you have this potential for Schwarzschild. How many of you have ever calculated the trajectory of geodesics in the Schwarzschild metric? Pretty much everyone. Everyone remember the potential? There's a little barrier. It's not an identical potential, but it's the same phenomenon that happens for these modes. So what happens if you take say, a right moving mode over here, and you sort of evolve it backwards in time, it'll have some probability of having come from this way and some probability of having come this way and then bounced off to come this way. And part of it is that you get some reflection and some transmission. And so there's a number of things you have to do that you can't even really do analytically in order to write down the gray body factors, which do impact the state. But we're not going to go through the details of that. I'm just going to write down the state, and I'm going to tell you which modes dominate. It turns out that the dominating modes are the L equals 0, essentially the S wave sector is what dominates. So we're mostly going to be approximating things that way. If you want to see the full derivation of all the gray body factors, the Jerusalem lecture notes do have all of that full derivation. Yes?
Is it obvious that this boundary condition that there's no infalling modes isn't some insane, maybe non-physical?
Just to have only ingoing modes? No, you could just say, I'm going to take an empty universe, and now I'm going to have a single shell that I throw into that empty universe, and nothing else ever after that. That seems like a perfectly reasonable system for me to study. In fact, stating that the black hole has stopped accreting is the statement that you don't have any more, that the left-going modes are all in the Rindler vacuum.
If I were to imagine
So that's if you start out with the Minkowski vacuum, you have to do something very violent to it to get here. But we're not starting out with the Minkowski vacuum, right? We're starting out with some pure state over here, tensored with a bunch of, with the vacuum here. That's an initial condition. Everything that you put on scry minus is an initial condition. So we just prepare an initial state. That's how we prepare it. We are allowed to prepare this initial state. It's not, I would not consider it to be an unphysical state. Yeah.
But that's sort of conflicting with this picture of it. I mean, when you say it's just one shell of matter falling in, what I'm imagining is I start off with a Minkowski vacuum with the correct number of creation operators to create something.
Mm-hmm.
But I'm starting in a Minkowski vacuum. And you're saying that's not what.
That's, yeah.
The usual setup for QFT, you're saying totally not that very, very far away. If you want to get this nothing falling in, you have to start with very.
Yeah, you start. It's a different state that we're starting out with. We're not building this up from Minkowski space. Yeah.
Then you start with the shell that goes outside the non-Minkowski. Asymptotically with us.
All right. Great. So let me write down the state. Oh yeah, question.
I mean, can you say it again? What is the condition for the black hole horizon to be smooth? I mean, it seems that you have like part of the modes, for example, the right modes to have the correct like entanglement structure across the horizon, but the left movers are just, I mean, in the ground state. Why are you saying that this also leads to like a smooth horizon?
So that leads to a very singular past horizon, which we don't have. There is no past horizon here.
Oh yeah, so the future horizon, like the smoothness of the future horizon is actually controlled by the entanglement behavior of the right mover.
That's right, and here's how to see that. So here, when we say we get a large divergence when we disentangle the modes, that's the divergence that we get is going to happen between the modes we disentangle. So to get a divergence on this right moving horizon, we have to disentangle the right movers. Now you could say, okay, my left movers are disentangled, but they're disentangled from something that doesn't exist because there's no past horizon in this picture. So what would happen if I were to say, okay, these two left movers are disentangled, then I would get some kind of a past horizon. Like, can you actually see this?
I can actually imagine that.
Does that answer your question?
Yeah, I mean, right.
Okay.
Thank you very much.
Okay. So let's continue.
There's a little more than 15 minutes left.
15 minutes. Okay. Like 20. Okay. So let me quickly write down the state. I'm going to expand it in terms of spherical harmonics. So this is after somewhere up here, after everything's equilibrated and long after the shell has crossed. So this is going to be the vacuum for the ingoing modes. And it's going to be tensored with essentially the thermal state for the outgoing modes. So this is going to be tensored over the spherical harmonics. Sorry, this is small. Over spherical harmonics, and the omegas here correspond to the frequencies. So I'm not actually going to use this form, but it's good for it's. I should write it down at least once. Minus beta omega and these are all outgoing. And again, this is dominated by the L equals 0. The low L modes are the ones that dominate this as a consequence of the potential barrier. All right, so using this, and by the way, I should mention there is an implicit time dependence here, which goes into beta. As the black hole shrinks, the mass gets smaller and beta changes. So even though this doesn't look time dependent, the time dependence is implicit in the temperature beta. Now, we can compute the energy flux away from the black hole, and just using the state. And I'm not going to go into the details of that because I am running short on time. We're going to approximate it with the L equals 0 modes because those are the ones that dominate. And this goes as -1 over the Schwarzschild radius. And now we invoke the fact that the ADM mass is conserved. And so the black hole must shrink. And the fact that this is the energy flux away from the black hole means that this is also the way in which the mass of the black hole, or the Schwarzschild radius, if you're worrying about how to define mass in GR, I'm just talking about the Schwarzschild radius, how the way that this is minus sign over here, this is the way that the mass behaves. And from this, you can compute how long it takes a black hole to evaporate. So T evaporation, this makes some assumptions about, for example, if you have something like a gas of photons, which is a thermal gas of photons, then T evaporation goes as m cubed. So there's a g Newton squared that goes into this to make it in the right units. So this is a slow process until late stages. But it is, so you can see, it speeds up at very late stages. But for a long time, this is a slow adiabatic process that nevertheless gets you to the point where the black hole eventually does fully evaporate in asymptotically flat space. And so this here we've sort of derived in a hand-wavy, arm-flaily fashion what I advertised at the beginning of the lecture, which is that we start out with a pure state here. We throw in a pure state, and we end up in a thermal state. And look, this thermal state pretty much only cares about beta. It doesn't care about all of the fine-grained details that went into this pure state. And so this is this statement that if we just accept Hawking's derivation of this, we find that we have a big problem in terms of determinism of physics. So the final state we're looking at the state on Scri plus. Scri plus union I plus.
Yeah. Well, and that's what we're at.
Yes.
Like you said, necessarily, it's clear that it's the same as the guy who sits next to the horizon.
Who says like here?
Yeah, that's what
that one will eventually make it out there. So there's an approximation here, which I think is what you're pointing out.
Well, no, I just mean like it's measured with respect to the timeline, that temperature.
Yes, and so there's a lot of subtleties that I've glossed over. In particular, there's one approximation which I glossed over, which is that, we were sort of Rindler here, but then what happens over here? And I'm actually going to get to that now. I guess I should put these down. Okay. So at the very least, by the end of this lecture, I can state the information paradox and what are the very unappetizing choices that we have. Okay. So, 3 options. So the first option is to simply accept the time evolution in quantum gravity is non-unitary. This is very unappealing and unappetizing because that means we lose information. So we lose information, we lose predictivity. This is what Hawking suggested. The second option is something I alluded to just now, which is none of these approximations really work when the black hole is microscopic. The curvatures are very large at the horizon. It's no longer true that it looks like Rindler. Maybe something happens there. Or what right do we really even have to say that it fully evaporates? Maybe it just shrinks and it just sticks around as some Planckian messy thing. That could happen. We can't really use effective field theory anymore to say what happens past that evaporation point or close to that evaporation point. So all this stuff in the black hole sticks around forever. in a Planck-sized remnant. This is a violation of the Bekenstein-Hawking entropy formula, because all of the stuff in the black hole being concentrated in this tiny Planck-sized region would be a gross violation of S Bekenstein-Hawking equals area over 4G. So we might have to give up unitarity. Another option is to give up the microstate interpretation of the Bekenstein-Hawking formula, microstate counting interpretation. And the third option is that EFT is violated on the scales on the event horizon of a large black hole, meaning on scales where energies and curvatures are small enough that we should have already seen such violations. Yeah.
Could you remind me why we should expect the area formula to hold for Planck-sized objects?
So you could say maybe the area formula does not hold for such Planck-sized objects. But if you expect that there's some kind, you can sort of circumscribe it in something that's a little bit bigger that would actually count the microstates. I mean, it would be grossly violated to the point where even if you go further out a little bit, so you could actually enclose it, it would still be grossly wrong. So this is a huge violation of this, not like one where you could say, oh, you know, maybe there's some fluctuation and kind of it's everything is small. The entropy would be huge and the area would be, we don't know exactly how to define it, but it would be Planckian. Yeah.
It's related to that. Does the fact that there are corrections to the formula that are like log equals 1 over a, does that
That would unfortunately not help us. Yeah. But sure, it will not be exactly the area. It will be area plus extrinsic curvatures plus other terms, which will not be enough to offset this. Yeah. Other questions? All right, so let me state the information paradox. The following three facts cannot all be true. The first is unitarity of quantum mechanics. The second is the microstate counting interpretation of the Bekenstein-Hawking formula. And the third is effective field theory on scales that we have already observed. Now, none of these is one that we like. We don't like any of these. But yeah, Manu.
Do you want quantum mechanics or quantum gravity?
Well, quantum gravity is quantum mechanics, so I can say quantum gravity if you prefer. Or quantum gravity is quantum mechanics. Okay, so unitarity. We don't like any of these. Now you might say, maybe we should like 3 the least. Maybe this is the one we don't want to lose. And the reason we don't want to lose it is because it's empirical. And yet, I am going to try to convince you that this is the one that we need to give up. And we're going to somehow have to live with the fact that EFT is going to have to be violated on scales that maybe we should have already observed, and we're going to have to explain why we haven't seen these observations. So the stakes are very high in the information problem. All of these seem like they're fundamental truths, and we need to give up at least one of them. Now, why do I say that we should give up 3? The reason I say that we should give up 3 is, well, there are many different reasons for it, but the one I like best is the ADS-CFT correspondence. So in the last few minutes, I want to give an argument for why in ADS-CFT we have 1 and we have 2. And since, ADS-CFT is our most well-understood quantum theory of gravity, and who cares about empirical evidence, we are going to stick with that and try to understand what are the consequences of unitarity, and how do we explain this in a way that is not going to contradict our empirical evidence. So, so in ADS-CFT, what happens? Well, and I will say that ADS-CFT made even Stephen Hawking concede that you couldn't really give up 1 or 2. So in ADS-CFT, we can say, all right, let's consider a situation where we have some black hole forms in ADS. Now, as we're going to discuss next lecture or the one after that, ADS black holes are a little bit annoying in that if they're large enough for us to understand their CFT dual, then they're too big to evaporate because ADS boundary conditions cause the radiation to reflect and feed back into the black hole. So the story of no left movers is not quite valid. Nevertheless, even though we don't know how to describe small ADS black holes in the CFT, they exist. And so whatever state we need to write down for the CFT to describe these small black holes, it exists. And so we can say it's a mystery for us what that state is. But this phenomenon does exist and must have a CFT dual. So this is an evaporating ADS black hole, which is small enough to fully evaporate before most of the radiation can sort of bounce off the boundary and make it back and reaccrete the black hole. And so if we sort of form this black hole from some pure state, then in the CFT, this whole thing is also going to be in some pure state. And then this is going to evolve forwards in time. And this will evolve forwards in time. And in the CFT, what this evolving forwards in time means is that now it's going to be this state, which is unitarily related to this one. And no information has been lost. So just ADS-CFT, just a statement that the CFT evolves unitarily at finite n, tells us it is unitary. There exists a quantum theory of gravity with unitary black hole evaporation. Also, ADS-CFT talk in terms of microstate accounting for the Bekenstein-Hawking formula. So you can match density of states in CFTs. In the CFT at large central charge, large energies, you can match the density of states to e to the SBH, which is the statement that we can basically reproduce the Bekenstein-Hawking formula. You guys may have studied this last week as well. We can reproduce it from the CFT. So ADS-CFT says Bekenstein-Hawking formula, and not just ADS-CFT, there are many other derivations of the microstate counting of the Bekenstein-Hawking formula, but specifically in the context of evaporating black holes, ADS-CFT suggests that this is also going to be true. And so we are going to have to violate effective field theory. Now, what we would really like is a way of understanding how ADS-CFT deals with that. And for a long time, this was a bit of a mystery. We were stuck on this for a long time. And in 2019, we figured out something that showed us that you could sort of eat your cake and have it too. You can have effective field theory in ADS-CFT, and you can still have unitary evaporation. And the analogy that I like to think of for this is that there exist other ways of computing quantities that require some quantum gravity input, but are, in some sense, semi-classical. Much like if you were to do a calculation of the pressure of a gas using only thermodynamics without knowing anything at all about statistical mechanics, you would look at the average velocity, and you would say, oh, it's 0, and so the pressure is 0. But if you looked at PV equals nRT, which is a formula that you derive from statistical mechanics, the pressure is not 0. So similarly to how there's this weird contradiction in effective field theory of thermodynamics, we are going to see that there's something that comes in analogously to that in quantum gravity. And so for the rest of this, I guess this lecture is now 30 seconds left in duration, so I'm not going to do much for the rest of it. But what we're going to pick up with next time is what are the consequences of unitarity How do we test unitarity? What does it mean to have unitarity? And once we're done with that, we're going to move on to talking about how we see 3, how we understand 3 in ADS-CFT. All right, I will see you all tomorrow.